Hi, welcome to 27 CICS channel. In this channel, we are going to publish videos related to CICS transaction server on ZOS. And this video is all about ZOS storage concepts. The reason for making this video is anyone who is interested to learn about mainframe or any subsystem on a mainframe. I think it's good to know the basics of ZOS storage concepts. And when we say ZOS storage concepts, we mainly talk about the types of physical storages we have and the concept of virtual address on ZOS and the address space. So let's begin. Yeah, here in this slide, what he's trying to show is the overview of a mainframe storage. Here we have there are two types of physical storages. One is the central storage and the auxiliary storage. So when you compare the differences, central storage is fast, and whereas you compare central storage with auxiliary storage, accessing data present on an auxiliary device is a bit slow. And when coming to the cost, the central storage is expensive and auxiliary is less expensive when compared to the central storage. And if you see, the mainframe is comprised of central storage and processing unit as well. So the processing unit is especially the one who gonna process the instructions which are present inside the central storage. Okay, and here the terms processor storage, main storage, real storage, and the memory, they are used synonymously, and they all present in the processor cache. So yeah, here these are like definitions of what does main storage mean. Like as we discussed, this is the fast access to the electronic storage or data present on the central storage. And when compared to main storage, auxiliary storage, it's a bit slow, and it mainly consists of the paging data sets which are required for handling the virtual storage concept. Okay, and the processing unit, as we discussed, it is the hardware which is in charge of executing the instructions which are located in the main storage. Okay, what exactly is this virtual storage mean? So virtual storage exactly is an illusion, okay, created by the architecture on ZOS, and by this illusion, what the system does is like it creates a image to the user, like as though you have a more amount of storage than you really have. Okay, so by this you can provide multiple users to log in and use the system, though you do not have enough real storage. Okay, and to make a more number of subsystems run on an LPAR, this concept is really helpful. And what exactly is the address space is it's a range of addresses in virtual storage. Okay, so anything and everything on a ZOS system is a virtual storage address space. Okay, that was the reason, like earlier it was even named as MVS. MVS stands for multiple virtual storage, and later they renamed it to ZOS. So like you want a subsystem to be up, it gets created as an address space, and you want to log into a LPAR, address space is created on behalf of you. So yeah, everything in ZOS, it runs as an address space, and that is a range of address provided by the virtual storage. And this concept is achieved by the combination of central storage and paging data sets. So what exactly he is trying to show here is you have two address spaces. One is for user A and one is for user X. Okay, and when user A wants to access um, this particular virtual address, and this is an example address here. So it goes and really fetches means there is a processing in between called as DAT. DAT turns into dynamic address translation. So we are not getting into that detail of how address is translated from virtual to real. But if you see, this virtual address is translated into real address of this, and it is accessing the data belonging to XYX. Okay, and in case if the address which he is trying to user A is trying to access is not present in the central storage, so that means it is already paged out. So inactive contents will be uh, paged out to the page datasets. So if you see here in this example, user A is trying to access this block of address, and he in internally there'll be a page fault which occurs, and then he'll be routed to the uh, it's the system fetches in the page datasets, and that storage or whether it could be instruction or a data, it will be again brought back to the central storage and then provided to the user. And all this is transparent to the user. User will not know like what is happening in the backend. So that is the beauty of the system. So he always feels like he's enjoying all these storage allocation, but in reality it's not. So whatever required will be fetched. The address will be translated into real address. In case if that is not found, then it is fetched from the page datasets and provided to the user. So this is how the virtual storage works. And anytime a user tries to access address, that is always a virtual address. User will not have any details about the real address that is internal to the system. Okay. Yeah, as we discussed, the virtual storage is an illusion created by the Z architecture, where the program seems to have more storage than it really has. And by that, like each user or a program gets an address space, and address space is nothing but it's a range of storage address, and only the active parts of instruction or a data are present on the main storage, and the inactive paths, they go into the auxiliary storage. Okay, and for example, you have seen this virtual address, right? So how exactly it is subdivided into bits, that he is trying to show here. 0 to 32 bit, that is called as region index, and 33 to 43, it is called as segment index, and 44 to 51, it is called as a page index, and 52 to 63, it is called as a byte index. So by using these tables in the backend, okay, which is transparent to the user, so for example, this virtual address will get translated into this real address. Okay, so these are the tables which the system uses in the backend. Okay, and as we discussed, like all the storage references made are made in terms of virtual storage address, not the real storage address. Okay, so having said that, like we have two kinds of storage, that is the central storage or the real storage and the auxiliary storage, and we have an illusion storage called virtual. So but all these storages are equally divided into blocks of 4K size. Okay, the block which is the 4K block which is present in virtual storage, it is referred as pages. Okay, and the similar 4K block, if it is present in the real storage, it is referred to as frames, and the same block is referred to as slot if it is present in auxiliary. So what we are trying to show in this picture is, if you see, for example, there's a program which is running in this virtual address, okay, and is subdivided into equal parts like A to H, okay, and when you fetch the blocks A, E, H, and F, you directly get routed to this real storage, and you user can access them because they are already loaded into your real storage. But whereas if a user is trying to access blocks like B, C, D, and G, so a page fault happens because first it goes and tries to search in the real storage, but a page fault happens because those blocks are not present. So then it goes and fetches from the page data set and then brings them back to the real storage and provides to the user. So all this process is again transparent to the user, but this is how internally it works. So a block of 4 KB of main storage is called as a frame, and a block of 4 KB addresses in virtual storage is a page, and a block of storage on an auxiliary device is a slot. Okay. And as we spoke about virtual storage or virtual address space, or a in simple terms, address space is a range of addresses in virtual storage. So uh, the Z architecture earlier in the olden days, it was provided, it was limited to 16 meg. Okay, later with new advances in the hardware and software, the limit was extended to 2 gig, and now with the latest hardware and software, it is even beyond to 16 exabytes. So having said that, below the line you have the 24-bit storage, and above the line you have 31-bit, and above the bar, that is 2 gig limit, you have 64-bit. So this limit 16 meg is called as a line, and the 2 gig limit is called as a bar. So you refer the storage above this 2 gig as above the bar, and the storage below as below the bar, and same applies here as well. So the below storage, which is below 16 meg, you refer it as below the line, and the above storage which is present above the 16 meg is called as above the line. And here he is trying to show you different ways this address space is made up of. And if you see, there are few things which are common, okay, and when I say common, it is shared across all the address spaces which are getting created on the ZOS subsystem, okay, and they're shared across all the address spaces, and the things which you see as a private, uh, they are specific to that particular address space and that particular user or a subsystem, okay. If you see, as I said, initially it was not designed for a 2 gig or beyond that, so the initial limit of a typical address space is 16 meg. So you see these nucleus, SQA, LPAs, and CSA, and once the architecture was improved, so the same names you can see, but they're tagged as or prefixed as extended, okay. Only thing you do not see or only see in below 16 meg is the PSA, okay. Rest, it's like a replica above and below the line. Okay, and having said that, like whenever a user logs in, he gets this kind of address space, okay. So he gets theoretically he gets a 2 gig of storage accessible, but in reality that amount of storage is not allocated to the user in the first front itself, or he may not even aware, right? He always feels like he has got a 2 gig amount of storage. So active paths, so it's all achieved with this virtual storage, okay, and active paths are only loaded into the real storage. When I say active paths, it could be instruction or it could be data related to that instruction, and the inactive paths, they are moved to the page data sets. Okay, so when someone a user or a subsystem tries to execute a program, not a whole program is loaded into the real storage. Only the instructions which are running at that point of time are loaded, and the respective data. Okay, so that way ZOS manages such a huge workload on mainframe. Okay, so here he is trying to show you multiple address spaces, okay, wherein some section of this address space is common. When you say common, that means that address is shared across all the address spaces, and the rest is the private. Below the line it's just private, and above the line it's called as extended private. So this way, when you take a look at the private storage, so that private storage is not shared across the other address spaces. That way, like it creates an isolation between different address spaces, so it creates some kind of security. So a particular user of one address space will not be able to interact with the or interact with the data related to the other address space. So in that way, ZOS improves its security, but there are times where you have to share the instructions and the data. So that is where this common virtual storage area comes into picture. Okay, so that way it provides protection, and wherever required, it even shares the information across address spaces. Okay, so when I say address spaces, it could be a subsystem address space, or a system address space, or a user address space as well. Okay, so here he is trying to highlight the private area of an address space. So this is the area which is really usable by a user. It could be a user, or it could be a subsystem like CICS or DB2, anything for that matter. But whereas the common part, it has to be shared across all the address spaces created in that LPAR. So yeah, this is the real area where we load our user programs and data, and execute and get the results. So that area is highlighted as in yellow color. You have a private area below the line and extended private area above the line. And to supplement the address space, we have something called as a data space as well. Okay, it is a bit different when compared to the address space. It doesn't follow the split up architecture which we have seen in address space, but it ranges from 0 to 2 gig, and we cannot store any instructions in a data space, but it is primarily used for storing data. Okay, the main players who use this data space are especially the monitoring tools. If you take CICS monitoring tools like OmegaMon, TMon, they exploit data space to store huge amounts of data. And there are other CSS tools like Kixplex, who is a big exploiter of these data spaces. And CSS itself is an exploiter of these data spaces, wherein you enable features like Kix data tables and other data tables. So this data space will be used by CSS as well. Okay, so these are the points which we discussed. So it typically ranges from up to 2 gig. Okay, and it's a contiguous virtual storage, and it's a bit different. The map of a data space doesn't look like an address space, so it's just used for storing data, and it doesn't contain any specific areas. Okay, so till now we have discussed how a typical address space in a ZOS looks like, and how it is achieved by the illusion storage called virtual storage. And if you see, The address space has a map, like it has below the line and above the line and above the bar as well, right? The line is limited to 16 meg and the bar is limited to 2 gig, and something beyond that, or the limit is 16 exabytes, that is above the bar. Okay, but what decides a program or a data to be resided above or below the line, or what address it has to extend up to? So that is all decided by this addressing mode and the residency mode. So in short, they are called as A mode and residency mode. Okay, let's start with the values 24 with 24-bit. Okay, and in case here, if you take the example of program B in this picture, so it is compiled as A mode 24 and R mode 24. Okay, compile and linkate it with these values. Okay, what that means is like this program has to be resident below the line, because you have mentioned R mode as 24, and the data it has to use is of 24 bits. Okay, so that is the data it gonna use. Even the data will be stored below the line, so that way these two palms decide where the program should be loaded and what data it has to access, what addressing mode data it has to access. Okay, whereas if you take the example of program A, here it is linkated with A mode 31 and R mode any. Okay, so R mode any means resident mode any, which means like the program can be loaded above the line or below the line. So that is the reason here showed in this picture, program A is being shown in the dotted line, like whether it can be loaded above the line or below the line. Okay, when coming to the A mode, it is given as 31. Okay, so the data is present above the line. Okay, it is 31-bit address is possible, as we have mentioned A mode 31. Okay, and you can see the typical address of a 31-bit and a 24-bit as well. If you see program A as it is defined with as it is linkated with A mode 31, you see the address as 31-bit, and whereas program B is linkated with A mode 24, so you see program B data is of 24 bits. Okay, so these parameters are important and they decide where a program has to be loaded and what should be the addressing mode. Okay, yeah, if you consider the whole an LPAR as a whole, so everything in ZOS is fully made up of address spaces. So if you see on the left hand side, he's showing the system and subsystem address spaces. Okay, so when you IPL a system, so these are the subsystem systems which are brought up, and they provide various functionalities like chess or catalog or trace or linked list, LLA, and all that. And on top, on top of it, once the system is up and running, so you can bring up other subsystems or starter tasks like TSO, CICS, VTime, DB2, XYZ, and even when you log in to a region, so address space will get created for each and every user. And even when you submit a batch job, that runs as an address space. Okay, with the help of initiators. Okay, so this is how a typical ZOS address space looks like. I mean, subsystem looks like, which is a bunch of address spaces. So yeah, as this channel is primarily focused on CICS education, so you might be interested like how a CICS address map looks like. So it has a bit more internal mapping when you compare with the default ZOS architecture map. Okay, So it is still more sliced into something called as DSAs. Okay, and again we have a couple of parameters which control a DSA limit, below the line and above the line, even above the bar as well. So this picture only shows about 24 and 31 bit storage, but this is how um, uh, the internal CICS storage is split based on EDSLM and DSLM sitpams, which we're going to discuss in other videos when we talk in depth about CSS. But this is how CSS address space looks like, apart from the normal general ZOS architecture address space. It is even subdivided as these DSAs, like CICS DSA, user DSA, read-only DSA, and share DSA. So each DSA has its own purpose in turn. So that we're going to see further, but this is just a glimpse. Okay. Yeah, as we are talking about address space and virtual storage, so in this picture, it just provides you a glimpse like how a program is compiled, linked, and executed. So let's start from the left hand side. Like after compilation, you get the object modules. So here he is taking an example of program A and program B. One is of length 80K and the other is 60K. So once you link it, they both combine together and form a load module. So 80 plus 60, that is 140K. So the whole load module is of size 140K, and it is stored in auxiliary storage, okay, inside a PDS as a member. And the name he chose is myprog. Okay, when you say myprog, it is comprised of program A and program B, and this is residing in the auxiliary storage. Okay, but anything and everything cannot be executed from auxiliary storage directly. Okay, both the instructions and the respective data required for that instruction or that program has to be loaded into the address space. Okay, so that is what happening on the right hand side. If you see, this is a typical address space map, okay, where the splits here shown at 16 meg, that is the line, and this is a 2 gig, that is a bar. Okay, so here the my program is loaded below the line, okay, and it starts executing. Okay, so that is how it works. So from compilation to execution. So yeah, that's it. Thanks for watching the video, and if you like this video, please make sure you like, share, comment, subscribe, and press the bell icon. And if you have any queries or training requirements, please feel free to email at this ID, and thank you.